Okay, let's go ahead and get started. I'm Charlie Smith, Executive Director of ESIG. I want to welcome you to our monthly webinar series and give you a little bit of background on ESIG. For those of you not familiar with ESIG, we are a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities in support of renewable energy and energy systems integration decisions. ESIG does this through workshops, tutorials, webinars, blogs, working group and task force activities, and technical resource materials. Our most recent activity was our annual Fall Technical Workshop, which was held online during the month of October and into early November. Our next major activity is our annual Spring Technical Workshop, which will be held online during the month of March. Our workshops and monthly webinar series are open to everyone, so please feel free to register anytime on the ESIG website. Our workshops deal with a full range of issues associated with integrating wind, solar, and storage into electric, gas, and thermal systems. They also deal with a coupling to energy-consuming infrastructures, especially electric transportation, buildings, and industry. ESIG is a very unique organization, and I don't think you'll find anything quite like it anywhere else in the world. If you're new to ESIG, I strongly encourage you to follow up with us if you like what you hear, and I think you'll be pleasantly surprised. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Okay, just a few logistical matters before we get started. First of all, the phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we have moved to the Slido platform, and we are asking you to ask your questions through Slido at slido.com. You will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter ESIG2 as the event code to ask your questions. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions to allow you to cast a vote to help prioritize the questions submitted. We plan to save 10 or 15 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, so today our webinar is on the topic of redefining resource adequacy. The webinar will provide an overview of the topic of resource adequacy principles, methods, and metrics with the changing resource mix. We will also present some preliminary modeling results. Based on registrations, it looks like this is another quite popular topic. The webinar will be presented by Derek Stenclik, who is a founding partner at Telos Energy, a power systems engineering consulting firm. Derek is currently leading a resource adequacy project on behalf of ESIG, which he will talk about. He was with GE Energy Consulting prior to starting Telos and has a decade of experience helping clients across the industry accelerate the transition to clean energy systems. I've known Derek for most of that time, and I feel very fortunate to have him here with us today. On a personal note, as I like to do, I took a look on LinkedIn last night to check out our mutual connections, and I found out that we have 122. So I guess we must share some common interests other than resource adequacy, Derek. But I have to tell all of you, he knows a lot more about resource adequacy than I do. I greatly value the contributions of Derek to ESIG and the industry, and I look forward to what he has to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG2 to ask your questions. Now, without any further ado, let's go ahead and get started. Derek, I'll turn it over to you.
All right. Great, Charlie. And appreciate the introduction. I think a lot of those mutual connections on LinkedIn are because of ESIG, and so you've probably made a lot more introductions for me than I have for you, and I assume most of the folks on the webinar today fit that bill, so always appreciative of ESIG and getting the opportunity to share some of the work we're doing here. So with that, I'll jump into the presentation. Again, we'll hold the questions to the end, so go to Slido so we can get those. We'll also have a couple polls embedded in WebEx here as we go. So again, my name is Stenclik with Telos Energy. I want to talk about the work that I'm doing really on behalf of ESIG around redefining resource adequacy for modern power systems. And we'll get into what that means here in a second. So before I do that, again, just want to acknowledge ESIG for helping support this project. There's also been several other folks, I listed a few of them here at the bottom, that have helped out with a lot of the thoughts and ideas in this presentation. So I want to make sure I give those folks credit as well. For those of you who are involved in ESIG in the past, I think you'll recognize most of those names as being pretty regular contributors to the ESIG space as well. All right, so I thought a great way to start a conversation about resource adequacy is the recent news. It's hard for almost everybody in the industry to miss the news coming out of California around resource adequacy and the rolling blackouts this past summer. Probably a big reason why we have such good attendance here today. I think resource adequacy in general in the industry is getting to be a lot more important, a lot more popular in the past couple of years, and the recent events in California just really highlight the need for the industry to really start to think about this differently. So I want to start the presentation today. I'm not necessarily an expert in what's going on in California, but wanted to touch on basically some of the trends that I see happening there that may be something we'll have to address in a lot of other regions as well. So to start with that, I thought a quote by Steve Burbridge right before he left as CEO of CAISO was a really great way to start. He summed up a lot of what I've been thinking over the past couple of years and really what brought this ESIG project together. So this project started about 6 or 8 months ago, well before the California event. And we were using some of the very similar terminology that you see Steve Burbridge quoted here saying. And he said, following up on that, the rolling blackout events back in the summer, there doesn't have to be a trade-off between reliability and decarbonization. What caused the August blackouts was a lack of putting all the pieces together. You have to rethink the old ways of doing things. And I think that's what didn't happen here. And then he went on to say the resource adequacy program in California is now not matched up with the realities of working through a renewable-based system, and in a nutshell, it needs to be redesigned. And really, that's something I've seen across the industry is the industry in general has continued to use the same metrics, the same methods around resource adequacy and reliability that we've all grown accustomed to over the past years and decades. It's been slow to evolve. And so I think what we set forth in this ESIG project to look at is to say, how do things need to change now that the industry is shifting so quickly? So that's really a good way to start this presentation. I think California provides a really good case study of why things need to be looked at differently, and then we'll go into a few ideas that we have and some of the things that we're testing out. So start off with what happened in California. I mean, it was an interesting event for a variety of reasons. It was caused largely because of record-breaking temperatures across the West. And so what's notable here is this was not a California-only event. It was really felt across the entire West. It was like the figure here of it being a heat dome and really impacted not just California, but all the neighboring utilities, the transmission operators. And that's really important when we talk about why this had an impact in California. We need to look beyond just California borders, look at the region. And that's something, a fundamental principle that we'll get back to here shortly. When you look at temperatures in California over that time period, the orange line here is August or over the past 35 years, and the orange highlights the 2020 values, the period of concern where basically there were rolling blackouts and different phases of emergency calls highlighted there in orange. And you can see it was the outlier across 35 years. And that really brings up a valid question. You know, when we as system planners try to design our system, we intentionally make the decision that we're not going to capture all of the events, right? And we've grown accustomed to 1 day in 10 year loss of load expectation. We'll get back to that here shortly. But that's another thing that really came out of this is this something that should be planned for? I'll kind of leave that as a question. And then the other question that falls out of this is, should resource adequacy analysis take into account climate trends? Is this really truly an outlier over the past 35 years, or is there an underlying trend that needs to be taken into account when we start talking about planning future systems? I think that's something the industry in general is starting to think about, but hasn't really answered. So kind of underlying trends may be changing, and we may need to take that into account. So drilling a little bit further into the California event, I've got a couple snapshots here. The one on the left, I pulled generation by generation type on August 14th. So this was the first day of load shedding. There was a subsequent day immediately following that of load shedding. So technically two events that were, side by side right next to each other. And then on the right, this is a plot coming out of a CAISO study. I've got it linked there, but the preliminary root cause analysis of what caused the blackouts. If anybody's interested in learning more about what happened, it's a really great report to look over and gives you a good summary of what happened. But essentially, there's a couple ways to look at this, but there's the load curve, which is the top of the plot on the left, or the blue line on the plot on the right. And then the net load curve. So after we take out the solar generation predominantly, that gives you the orange line. And I bring this up for really two reasons. When we think about, when California thinks about its planning reserve margin, it's based off of the peak load, or the midday peak gross load. And historically, it was always the case, or almost always the case, that the peak load event was the most at-risk hour. Going back to kind of conventional resource adequacy analysis, when you have a predominantly fossil-based system where those resources are, in general, there's no time of day issue with a thermal-based resource. That's where California set its planning reserve margin. And when they do the resource adequacy analysis and take that into account on their PRM, it's looking there, and they assign some level of solar capacity credit, or effective load carrying capability of the solar during midday. What you see is the load shed events happened in the evening peak. So as the sun set, the load was much lower, but the resource, the supply, was also lower. And so there's a growing disconnect here that we're seeing between planning reserve margin and reliability. So something needs to change. One way to look at this is you could change the planning reserve margin as opposed to just looking at the gross peak. You could change it to an evening peak. But what would basically I advocate for with some of the work we've been doing is really that all hours matter when you're doing resource adequacy analysis. It's no longer just about the peak load. So we have to look across all hours of the year. And we shouldn't presuppose what the riskiest time periods might be. So our risky periods are going to shift with the shifting resource mix. We should plan for that, and whatever resource adequacy methods we use to really take that into account. It also drives the need to look at multiple weather years and chronological operations. So we'll get into that in a little bit more detail here, but what happens during the midday may affect what happens later in the evening. And historically, in resource adequacy analysis, the chronological operations of the system didn't matter as much as, do you have enough resources available to serve the load? Then it's kind of up to the operator to make it so that the system can respond. I think that's also a trend that's starting to become more important. What I see as fundamentally for the modeling community that's on the call, we're seeing a convergence between production cost modeling or operational modeling and the resource adequacy planning. All right, I like this, and again, just taking out another CAISO quote here. Could this have been predicted? And actually, if you go back to the 2020 Summer Loads and Resource Assessment, again, this report comes out before the summer season to make sure to quantify if the system is prepared. And if you look over that, this is kind of one excerpt. The event sort of was predicted. Basically, if they say, if you assume lower levels of imports into California, there could be reliability challenges, specifically late in the summer. Again, late in August is when this occurs, and later in the day when solar generation is near or at zero levels. And then specifically, they went on to say, we're covered for that, but if a heat wave occurs that impacts a broader area than CAISO, the availability of surplus energy to import into CAISO could be diminished. I think that's really telling. It was predicted. I think people are starting to see the trends. The other thing you'll see kind of from a political dynamic in California, the CAISO, the system operator, is not responsible for resource adequacy from the reliability perspective. That responsibility lies in the California Public Utilities Commission. And so you start to see a disconnect between some of the modeling that's being done on both sides of that fence. And so you start, it becomes an important dynamic of how different entities are approaching this. Again, that was written in May, so a few months before the actual event. Another good one to read, kind of how they're anticipating this. A lot of other good information in those reports, kind of looking at root cause analysis of which of the one of the first August 14th event was precipitated by a generator going on outage, a large gas generator. And although you hear a lot of the news kind of pointing fingers solely at solar, I think one thing that comes out of that we'll get into more is that there's no perfect resource. There's pros and cons of each resource. And as you start drilling into some of the root cause, you'll see that more and more. So what can we learn from California? Again, I just mentioned that in the media and a lot of the news, you saw a lot of the blame was placed squarely on solar and some of the renewables. And what I think is important to call out from that event is solar and wind output was 10 gigawatts during the peak load. And so there was actually a lot of generation during the system gross peak. And those resources effectively lowered the peak demand and shortened the window of the peak. So it provided a lot of capacity value, and without those resources, things could have been much worse. This is kind of just another perspective to look at that. The other one is ELCC, or the capacity value of solar. That metric is designed to quantify the average amount of risk that solar PV avoids, but the average doesn't always matter. We need to look beyond just average values. For example, take this to the extreme. If solar had a 50% capacity value, for certain that it'll provide zero capacity at 9 p.m. when it could be needed. So the planning reserve margin and ELCC in general kind of misses this obvious point. And so it doesn't take a rocket scientist or kind of a planning engineer here to know that the solar is not going to be there after the sun sets. And yet, when you look at how planning is done in a lot of regions still today, it really misses that completely obvious point. And I think that's something that, as we start to redesign the way we look at resource adequacy, we have to start thinking about that more. And again, going back to the Steve Burbridge quote in the beginning, the California event was not a renewables problem. We know kind of with some certainty at certain times of day that there won't be some renewables. It's more of a planning failure of how do we make sure that, given what we know about these resources, how do we make sure we can design a system around that? So again, I use that as a kind of a good case study to really start off this discussion of what is changing, how is resource adequacy changing. I think a lot of the changes that we're seeing in California and a few other places that are a little bit further in the renewable integration space, I think some of those challenges are ones that we're going to see permeate through other regions in the industry. So it's a good case study of how can we get ahead of this, both in California and the rest of the industry. And really, how do variable renewables, demand response, energy storage, and fossil retirements change the way we need to look at resource adequacy? So how is this changing? Conventionally, for those of you that are joining that are new to resource adequacy and are kind of wondering what I mean when I say that and why I'm being a little bit specific with some of the terminology, is essentially what that refers to is, are there enough resources to serve load when it is needed? That was kind of the conventional definition of resource adequacy. And from a historical perspective, for the past several decades, that really looked at two pieces. There was uncertainty in the load. You had load You weren't exactly sure what your peak demand would be or what the load would be, and it could change from year to year. And then there's also uncertainty in the supply. And historically, this focused most attention on generator outages. You have these really large centralized fossil plants. They had mechanical failures that could bring down the entire plant due to a single outage. And so you could lose, call it 500 megawatts because the generator goes on an unexpected outage. And a lot of the historical resource adequacy work focused solely on what is the probability you have multiple unrelated outages or uncorrelated outages of these mechanical failures occurring at the same time. And there's some recognition, you go back to the kind of the historical perspective of resource adequacy, there's some recognition that weather can affect both the load and the supply. So if you have variable renewables, the weather affects that, and there's some recognition that in a heat wave you could have more generator outages on the conventional thermal fleet. But that perspective is changing, or I will say has changed considerably in the last few years. So a new paradigm is really emerging. One, it was over the past few years or several years, it was driven first by the introduction of variable renewables, so wind and solar. Now we're not as concerned solely in outages in terms of when plants will go on full outages, but rather natural variability in those resources and how can we start to predict that. The second, this is becoming more and more important and is really where we've started to focus on some of this analysis for the ESIG project, is on energy limited resources. So specifically energy storage and battery energy storage specifically there, but also demand response. And so these resources, unlike wind and solar and the variable renewables where you're concerned about just natural variability in the resource, here with battery storage, for some certainty that you can have a certain amount of generation when you need it. The challenge becomes how long does that last for? If you have a 4-hour storage resource or a 2-hour demand response product, you can't necessarily cover an entire event. You can cover a portion of it. And so we start seeing duration of resources and the capacity shortfall events become more important. And then there's also an important aspect of forecasting the utilization of those resources. So how you determine when to charge and discharge the energy storage, or when you start to call on demand response, will impact how your options later in the day, later in the week, later in the season. And so now chronological operation starts to matter a lot more than it did in the historical perspective. The third thing we're seeing is just a shift in general to modular technology. So in the past, where you have large centralized fossil units, there's risk in discrete outages taking down 500, 600, 700 megawatts at a time. Now we're seeing a shift to modular technology, whether it's wind, solar, batteries. The probability of losing an entire plant is dramatically reduced. You may only lose, for example, one battery pack, or you might lose a few individual wind turbines, but the probability of losing an entire plant is dramatically reduced. And so the way we think about resource adequacy, I think there's going to be a gradual decreasing emphasis on the probability of generator outages and an increasing emphasis on all of these other aspects. The fourth is load flexibility. So the historical perspective always said our load is here and we need to match that with supply. And I think now we're seeing a lot of flexibility on the other side of the equation, and it'll just become more and more important. So the ability to shift load, to use load more flexibly, or to use demand response is going to become is really fundamentally changing the way we think about resource adequacy. And I think that trend will continue. And then the fifth is the potential for correlated events. So historical perspective, again, just assumed you had all these random generator outages and we just wanted to look at when those are likely to occur. I think now there's growing recognition that correlated events are what is the real challenge. So whether it's correlated weather, like we saw in California, you had a correlated weather event across all of the West. if it's a polar vortex in the Northeast where you have correlated events that could cascade to multiple generators, or correlated wind and solar generation events. That's the fundamental challenge now. It's not this random probability distribution of generator outages. So we wanted to, for the ESIG project and for what I'm going to present today, wanted to really take a fresh look at resource adequacy. And starting from a blank canvas, we asked ourselves a few questions. If we started from scratch, how would we evaluate resource adequacy for modern power systems without decades of inertia? Inertia is probably not the right word with this form, but without decades of precedent in how we approach this, is there a better way to do things? And specifically around wind, solar storage, and load flexibility as the fundamental drivers of that change. And then, what are the first principles, and how can we design a resource adequacy construct or change a resource adequacy construct that works as well today as it will, 10 years ago and as it will 10 years from now, and really kind of take the technology piece of it out and start defining things more from a methods perspective, regardless of the technology at play. And really the focus of this work in general is bridging what I see as a gap from the planning engineers that are in the utilities and the ISOs and other places with the policymakers and the regulators that are fundamentally kind of tasked with making sure their constituents are getting the reliability they expect. So the result of that process, I'm kind of boiling all of that together onto one slide. And some of you will recognize this from a blog post I wrote for ESIG earlier in the summer. But basically, we came up with originally 5, kind of new to today's presentation is a 6th principle of resource adequacy for modern power systems. I touched on some of these already, but I'll kind of discuss each one of these in detail right now. The first is load participation fundamentally changes the resource adequacy construct. So we're seeing, an increase in demand response, an increase in, and this can come from whether it's kind of controlled demand response or it's just time of use pricing or real-time pricing naturally changing behavior. It could come from electric vehicles having more flexibility on the system of when that load occurs, and just in general, more ability for system operators and consumers to change their load behavior based on system needs. And if you look at it from a consumer perspective, their willingness to participate or change their load becomes a lot easier if they have more technology at their disposal to either automate that for them or make it very transparent when and where they're using that electricity. So I think kind of growth in load flexibility really changes resource adequacy. And if you take that to the extreme, resource adequacy is no longer a reliability challenge where you risk reliability of the system. It's just, it all boils down to an economic decision of what price are you willing to consume electricity at. The second principle, modeling chronological operations is essential for modern power systems. Depending on where you are, resource adequacy analysis is already, in some places, taking this into account. You still do see places where they're only looking at, historical peak load periods for their resource adequacy analysis, or they're looking at many hours, but they're not necessarily looking at chronological commitment and dispatch decisions that, again, become a lot more important when you have energy limited resources. So again, I said this before, but seeing a confluence or production cost modeling and operational analysis really coming together with resource adequacy and planning analysis. I see those two really converging, and stochastic production cost analysis for the modelers that are joining the call. I think that's where the crux of this new resource adequacy analysis needs to go. The third is quantifying size, frequency, and duration of outages is critical to finding the right resource solutions. I'm going to spend most of the rest of this discussion talking about that third principle, but basically understanding more about these capacity shortfall events. The resource adequacy analysis in general is all about determining the probability of not having enough resources to serve load. And historically, it's focused specifically on loss of load expectation, or just the frequency of, or probability of those events occurring. And I think we need to know a lot more about those events if we want to design our system appropriately. So understanding how large those capacity shortfall events are, how long they'll last for, that's going to be critical to really making sure you can right size the right mitigation for the reliability risk on your system. The fourth is there's no such thing as perfect capacity. So I think we as an industry need to start acknowledging that all different types of generation has benefits and limitations. And I think this is critical. There has always been a historical mindset that a gas turbine was the only answer for reliability. And when you looked at planning reserve margin, you design your system and say, okay, how many gas turbines do I need to get this system reliable? I think that mentality fundamentally needs to change, and just really look at it from a technology neutral way to say, there's no such thing as perfect capacity. Everything has its limitations, and let's design a system that properly takes those limitations into account, whether it's fuel availability, whether it's ambient D rates on kind of fossil machines, or it's variability in the weather resources, or duration limitations in storage. I think that captures number 4. Number 5 is the reliability criterion should not be arbitrary, but transparent and economic. So what do I mean by that? Historically, loss of load planners design their system to meet an LOLE of 1 day in 10 years. So from a statistical perspective, you would have 1 day or one capacity shortfall event every 10 years, or a 0.1 days per year. Another way to look at that's commonly traded off there. But basically, that was always the line in the sand, and you had to design your system to get there regardless of the cost. And I think it becomes much more important to really understand what does that level of reliability cost us, not necessarily saying that it should change or we should change that criterion. We should just be much more knowledgeable about what that costs our ratepayers, and start to understand, well, what are the costs of going beyond that and getting more reliability? Is it fairly small? Then maybe we should do it. Or what is the cost of falling short of that reliability criteria? If it's significantly less expensive or there's other options there, I think that becomes more important. And the 6th, this is a new one for those of you who tuned into one of my previous presentations on this topic, or saw the blog post, is neighboring grids and transmission are key parts of our resource adequacy challenge, and both in terms of key parts of the mitigations and the options to improve reliability, but also a key part of the reliability risk. And we saw that play out in California this year, of seeing a regional event cause disruption. But I think in general, it's both a very valuable tool when we talk about improving reliability, but something that we really need to analyze in depth. So if for the resource adequacy planners on this call, making sure you're not just looking at the reliability of your system, but also of the systems around you in a probabilistic manner is important. So for the ESIG project and some of the things I'll present the remaining 15 minutes or so here. Oh, yeah, thank you, Ryan. I want to pause there and actually ask a poll of the audience. So you should have seen a pop-up come across the WebEx screen for a poll. And really what we're looking for from all of you is to vote on one of these that you think is the most important. Obviously, they're all important. It's like your children, but you got to pick one. So if you could go through and vote here right in the WebEx, and we'll come back to the results of that in a couple slides. So thank you, Ryan, for getting that up there. We'll keep that open for the next few slides and circle back on it. So how do we want to test these principles? And the idea here was, can we illustrate those principles and test them on a system doing resource adequacy analysis? And even when we started doing this, I said, maybe we look at a place like California. And that, again, that was before the rolling blackout events. And we decided kind of as a group for this ESIG project was, you know what, as soon as we pick a region, people are going to say, well, that applies to California and it doesn't apply to us, or that applies to New York, but we're different and it doesn't apply to us. So we wanted to kind of take a neutral approach to that and start doing analysis and testing out some of these methods and ideas on a test system. And then the idea being there, kind of perform the analysis first on a test system, show that it works, show that new metrics and things work on a test system, and then really look to the ESIG membership and all of you to start taking some of the learnings that we have and are going to present and take that back to your system and implement it on your utility footprint, your grid, your ISO, to see how it applies there. So what do we just, so for this analysis, really going back to the RTS-GMLC, so Reliability Test System Grid Modernization Lab Consortium. So this is coming out of the DOE labs, and it's really building on the IEEE test system. So the starting point of that, kind of going back to 1979, the IEEE Reliability Test System, which was updated in 1996. And the GMLC said, well, it's time for another update of that. And so you can kind of go, if you just Google RTS-GMLC, it's a public data set. Anyone can go onto their GitHub repository, get this data set. And the idea being it's a more modern test system that brings in a lot of solar, wind, and some of the chronological aspects of the modern power system. Still, though, for this analysis, we took that as a starting point. We added a lot more demand response, a lot more energy storage to modernize it even further, and then also brought in a lot more stochastics into that equation, so looking at different weather years and things like that. So the idea being we now have a test system. It's geographically, you can see it's overlaid in the desert Southwest, so kind of Southern California, Arizona, and Nevada. But really the only reason that's overlaid on a geography is to get a underlying weather pattern for the wind, solar, and load. That's kind of natural. And where are we going with that? Again, I said we took that RTS-GMLC data set that any of you can get access to, and then we augmented it. And to do that, we added a lot more solar and storage, a lot more, we added battery storage to that, and went back and added a lot of demand response. So, and when we did that, also, in effect, retired a lot of fossil generation. So added a lot more variable renewables, a lot more energy limited resources, and started retiring the fossil fleet. And really used those two cases, the out-of-the-box RTS-GMLC dataset and this scenario 2, as kind of two examples that we can start doing our analysis on and looking at two different systems for resource adequacy work. Again, that was at first centered over the desert Southeast, and we are kind of in the process of also, it was out of the box in the Southwest. We've also taken the approach of just transposing that same system into the Southeast and getting weather data in the Southeast. Again, this is a dual season peaking, both winter and summer peaking, a weaker solar and wind resource. So wanted to make sure that whatever we come up with, whatever the results of that analysis are, we can also kind of translate that to other geographies and make sure some of the methodologies and the results make sense there as well. So I'll pause there. Ryan, do you want to flip the poll or close the poll and show the results?
Yes, it's closing in 10 seconds.
All right. So folks can still get in there and make one last vote. All right, so it looks like chronological operations is the most important, kind of followed by we'll call it a three-way tie between load participation, chronological operations, and transparency in the economic criteria. So interesting, not too surprising, I think, for those of you on the call that are involved in modeling are all seeing this trend in kind of the chronological operations matter a lot more, not just from a variable renewable perspective, but also from energy storage and demand response as well. All right, and Ryan, you want to open up the next poll while I introduce it? So I'm going to spend the next, we'll call it 10 minutes, because I know we're running short on time, looking at new metrics for resource adequacy. And do we need new metrics, deeper metrics, just a combination of metrics? That's what we want to look at now. So for all of you, what resource adequacy metric works best for a decarbonized grid? Where do you think the metrics need to go? Planning reserve margin, keep it simple. Loss of load expectation, 1 day in 10 has worked thus far. Switch to something like expected unserved energy, or EUE, because we need to start knowing more about how size is important. And lastly, none. Scarcity pricing is all we need. So there's no need for resource adequacy metrics at all. We can just rely on pricing. So go ahead, start voting. We'll leave that open as I start going through this section. And then we'll see if maybe I influenced your response there. So yeah, one of the first principles was about quantifying size, frequency, and duration of outages and how that's becoming increasingly important. So here, just a very simple illustrative example. Again, I know sometimes resource adequacy analysis gets to be like alphabet soup, but wanted to show a few examples and how these metrics can show similar and also very different results. So on the left here, the left-hand side of this chart, I showed two examples of a capacity shortfall event. You have hours going across to the y-axis or the x-axis, megawatts, or the size of the event on the y-axis. You can see the top, both of these events are 4 hours in duration. They're both a single event. And that's here, the LOLEV denotes an event, not the average of all the events over all the cases. This is just one event. But you can see they're very different in how disruptive they are. The top event is much larger, both from an energy perspective, the maximum amount of load that's unserved. So even though, if you look at LOLE or loss of load hour, LOLE or LOLH, loss of load hours, they would show the exact same event, but you can see very different. If you extrapolate this onto a power system, one would be much more disruptive. The second example on the right, again, here you have the loss of load hours is the same. The EUE, the expected unserved energy, is also the same, but you have, again, very different events. The top one being 3 disparate events. So the frequency is much different, but and the bottom one is a single event. So really here, it's highlighting that we need to know more about what these events look like. And obviously not all events are capacity shortfall events are created equal. And I view, and when we start thinking about demand response and energy storage, some of them will be very effective at solving some of these events, some of them not as much. And so we need to start drilling down into these events and really understanding them more. So kind of drilling down on that one step further is, again, loss of load expectation and loss of load hours are good at quantifying the frequency of capacity shortfalls, but not necessarily the magnitude or duration. So it just tells you how often are these capacity shortfalls likely to occur. The benefit of that is the industry is really well accustomed to 1 day in 10 or the 0.1 days per year metric. I think and some of the reason behind that, and California is a great example, I'll argue the size of the event really didn't matter. It was just the fact that there was any load shedding at all really made the news and made this a very political event. The overall event itself was a couple hours in duration. It was rolled across the system, so most customers weren't affected for more than 30 minutes. So the actual event itself, I would say, was not too disruptive relative to distribution outages or wildfire outages and things like that. It's just the fact that there was an event that was critical. So obviously, in that sense, just calculating the frequency is important. But then you have expected unserved energy as another metric. Does a great job, or does a good job at quantifying the magnitude of shortfalls, but you get no sense in the frequency or duration necessarily. So I think there's starting to be a recognition that it's a preferred metric when we get into EUE, but again, even that has some limitations. So where I see this going is a combination of these metrics is going to be important moving forward. But there's still a limitation when you look at LOLE, LOLH, EUE. They're all still expected values. So they're giving you the average over many, many years of simulation. They're not giving you any more detail onto the distribution of those capacity shortfall events. So here's an example. Again, this is coming out of the modeling where you can have a system that has the same LOLE of 0.1 days per year, but then when you look at, okay, when we have simulations that had capacity shortfalls, again, so the first column there, the average, that's across all of the simulations that you do, and it's giving you the expected value. So if you run 500 years of simulations or 500 replications, what is the average across all of those? And so that's your kind of conventional LOLE, LOLH, and EUE expected value metrics. But then if you start drilling down and saying, well, if you have an event, what do those events look like? I think that's where you start to see things can diverge quite a bit, and especially when you look at these extreme events. And you can have systems with the exact same LOLE, but very different underlying outage properties. And specifically what you start to see happen is if you take this to the extreme and go to a system that just has 4-hour storage and energy limited demand response, you'll see resources effectively reducing the number of events because it captures the short duration ones really well, but the outliers events can become a lot larger. And so it's something that I think as planners, we need to keep our eye out, not just on the expected values, but on the full distribution of events. And another way to look at that, again, coming out of the simulations, is starting to look at when you have an event, what does that event look like? And so here on the left plot, I have the duration of those events in hours. On the right-hand chart, it's the megawatt hours per event. And what you see, and you can start to get very different underlying distributions of capacity shortfall events. But it's really important that you start looking at this, because if you look at this, I'll take scenario 1 as an example, and you draw a line up. This is a cumulative probability function. So it's telling you how many of the outages are 4 hours or less, where I've drawn the red line. And you can see that on the current system, the vast majority of all outage events, almost all of them, are 4 hours or less in this system. So what that tells you is that you don't need to go out today necessarily and build a new gas turbine. You can maybe go out and have very strategic energy limited resources will have a lot of capacity value. But what this is also showing is eventually those energy limitations will start to catch up to you as you start to retire more and more fossil, and you're going to need longer and longer duration resources. But still, you're in this realm of, pushes it out to 6 to 8 hours to capture most of those events. So it's really important that we kind of move beyond just the expected values and start to look at what do these events look like, and that's really going to help us right size the resources and the mitigations to fit the needs of the system. I have a couple more slides. I think I'd rather open it up to discussion, but really where I think this work is moving, and maybe it's a good segue into where the next presentation will pick up, is where does this break down from a planning perspective? And if you look back at how resource adequacy work is translated into making decisions on procuring capacity, there's typically a resource adequacy criteria. I have the 1 day and 10-year criteria here, and that sets the criteria. You run a bunch of resource adequacy analysis to quantify the reliability of a system, and then you do a translation of that resource adequacy analysis into the capacity of procurement. And typically in most places, or historically, that translation of resource adequacy into procurement was done with the planning reserve margin. So basically, you need to have a 15% reserve margin or 115% of capacity over peak load as a way to translate resource adequacy work to building stuff, whether it's in a capacity market or it's a vertically integrated utility procuring resources in an IRP. That planning reserve margin is the bridge between the resource adequacy work and procurement. And when variable renewables came along, ELCC, or capacity value, was really used to bridge the gap to make resource adequacy analysis fit into the planning reserve margin now that you had variable renewables. In my opinion, that was kind of a quick fix. It worked really well, or worked well for wind and solar, but there's limitations on continuing to use the planning reserve margin moving forward. ELCC is an expected value only. It doesn't capture all the differences. It's not really well suited for storage and energy limited resources because it's so dependent on the rest of the system. You can still use it, you can still quantify it, but it really depends on how much solar you have. And so you're just stuck in this iterative loop of always making sure you have up-to-date ELCC values. And so I think this is where a lot of the focus needs to be done, is really on this translation. So I'm actually going to, with 10 minutes left, pause there. Before we, want to say thank you to everyone for participating. I have my contact info here if you want to reach out. There's also a link to the ESIG. I'll have Ryan, if you want to close the poll and show us the response. We'll see if I swayed the votes there at all. And really want to open it up to the discussion. So let's see how the poll here did.
5 seconds.
All right. And remember, while we're waiting on that, you can go into Slido, put in your questions, and you can also vote on which questions you want to be answered. Okay, and good. I see that the polls are in. Expected unserved energy. Again, I think that's what's trending in the industry right now. It does certainly a better job at capturing a lot of the challenges I showed. Ultimately, where I think I will, I don't know about the industry, but where I will end up, EUE is preferred, but it's going to come down to a combination of metrics and really drilling down into not only the expected value there, but also the distribution. So thank you for voting. Very helpful.
Okay, Derek, thank you. We've got a lot of good questions lined up here. I think there's some interference with both of our mics down, so I'll try to keep mine off while you're talking. So let's go to the first question there. Isn't the issue that RA is now an energy rather than a capacity issue, and it must be tackled through the energy market where demand can participate?
Yeah, it's a good question. I agree that we are now moving, I like to call it energy first planning, where there's, it's not only do you have enough energy, though, it's do you have it at the times that you need it. So it's certainly one approach. I think what this question is referring to is moving that to, if you have an energy-only market, it's just going to be reflective of prices, and then you just, real-time pricing or even if you don't have real-time pricing, price scarcity events will be the incentive to make sure you have resources aligned with when you need them, and then also gives a clear incentive for demand to line up more with when the resources are available. So I certainly think that's ultimately that's probably the end goal. And obviously ERCOT and places are doing that today, and it's working. You do run the risk of, what happens if you don't get it right, and there is a capacity shortfall event. But ultimately, Yeah, I think demand is the place where this is going to be, resource adequacy and reliability is going to be solved. I'll say that demand can still participate even if it's not in the energy market. So whether it's in a capacity market or it's just in a procurement decision, demand can still be a big part of the resource adequacy puzzle and provide capacity. So yeah, I agree with the sentiment of the question. It's not necessarily the idea of firm capacity. I almost cringe when I say that because I don't think that's a relevant term moving forward anymore. It's just because we don't need firm capacity. We need to have energy available when it's needed, and then we need to have demand to be flexible around that as well. So.
Okay, good. And a related question from John Simonelli. Isn't it more an issue of having enough flexible resources rather than RA in the off-peak hours?
Let me think of how to answer this. So I think, yeah, it's a similar answer to that first question. I still view flexibility and ramping as distinct services to the resource adequacy capacity perspective. Ultimately, the way I like to think about all of this is on a spectrum of grid services. And when we talk about resource adequacy and capacity, that's just should be defined in a similar fashion of all the other grid services, ranking from inertia and then fast frequency response on the very short duration but fast speed of response side of a grid service spectrum, all the way to the slower responding but longer duration needs of grid services on the capacity side. And then flexibility and ramping is a grid service that's maybe somewhere in between. I will say that I think very shortly, if we're not there already in some places, the flexibility constraints, the ramping constraints, the regulation constraints, kind of those grid services are going to be largely solved by battery storage. It's not going to take too much storage to completely saturate regulation and ramping constraints. And then we're going to be left at the two sides of that grid service spectrum. And I think those two sides of those spectrums haven't been fully solved yet. And that's why I've focused so much of the work on the resource adequacy side is I do think duration of response is going to become more important. And just, if you have multiple days of low solar or low wind, is the energy storage going to be capable to get you through this or not?
Okay. Thank you for that. A lot of good questions here, Derek. I'm just going to go with the next one. How do you account for the impact of extreme weather and climate change on mid and long-term power system planning?
Yeah, good question. So I think the way I start to approach this is the first thing that's useful is when doing the resource adequacy analysis, make sure you're taking in many years of weather data, as many as you can, to make sure that you're getting at least the historical weather extremes taken into account when you're doing the analysis. Again, going back to the California example, when you look at the way their planning reserve margin is set, it's using a P50 or 1 and 2 load forecast for that. And I think, potentially misses some of the extreme weather events. So that's the first thing that we can do to at least get the historical perspective in extreme weather events. The next challenge is, where do you take that into if we're starting to see trends in moving in the kind of more extreme weather? So certainly you could increase when you're doing the resource adequacy analysis, you could increase the probability of those extreme weather events happening. So you can take your extreme weather year and have that occur more often than the average over time is one way to approach that. I guess the verdict's still out to me in how far we want to go and be speculative down that, or I guess I'm not the climate scientist. It's certainly something that we'll want to keep an eye on. I think there's a good way to implement that into the approaches that we have now. It's just a matter of what you assume for that trend moving forward.
Okay, we'll stay tuned on that one. Next question. Where does increasing the power of energy and ancillary service price signals as an ERCOT's energy-only market fit into principles for ensuring reliability?
Yeah, I think that fits into the principles is really on that first one in load flexibility. Because ultimately, if you have enough load flexibility, all you need is the price signal to make sure load can react to that. So I think that's where the energy-only market example from ERCOT, having those basically the market is relying on price scarcity events for two things: load participation to come in and basically voluntarily shed load. And the second is to set a clear signal of when and where resources are going to be needed in the future. Now, I think where that breaks down is if you go back to 2019 in ERCOT, where you had a ton of price scarcity in August and September, certainly drove up prices. I think there's a lot of folks out there, a lot of developers looking and say, if we just had a 2-hour battery resource, we could make a lot of money. That works really well for saying where and when and how large of an asset would you need to mitigate some of those challenges. The challenge is when you go to get that project financed from a bank and they say, well, you're asking me to bank a 20-year asset on 6 days of operation from an extreme weather year. I think that gets to be more challenging, and the reason why maybe that the economist inside me wants to go directly to an energy-only market, but the reality of what's on the ground makes that a little bit more challenging.
Okay. I realize we're running over a little bit for everybody on the line. There are a lot of good questions, and I think I'll just take another question or two because they are quite interesting, and if you want to hang on for that, that's great. If you have to run off to the next meeting, that's fine too. Okay, so the next question, Derek, is what time horizon should we model chronological dispatch for? Kind of a question and a comment. It should be long enough to deplete short-term storage, I think.
Yeah, so I would say we need to model the full chronological, every hour of the year. I think for a resource adequacy analysis, we don't need to get into, the sub-hourly or the really short time frames. Obviously, that's still important for the rest of those grid services I was discussing and making sure you can actually operate the system. But from a resource adequacy, do you have enough resources available? I think going down to hourly is probably the right resolution, but then doing that across a full year of operations is important because you do need at least the hourly resolution because that's how you're going to differentiate between 1 hour demand response product versus a 4-hour storage versus a 6 or 8 hour storage. So I think that's the answer there.
Okay, let's take one more question. This is from Yulia Matoiva-san. And it's as much a comment, I guess, as it is a question, and maybe you can comment on her comment. We find that storage duration and makeup of hybrid resources, as well as their participation in ancillary service markets, makes it increasingly hard to consider these in RA.
Yeah, good question, Julia. Good question, comment from Julia as usual. I totally agree. The storage duration is critical, and that's kind of pushing the reason why we need to start shifting to chronological operations. And certainly being able to differentiate between a 2-hour resource, a 4-hour resource, a 10-hour resource gets to be critical and will change over time. So as you see the resource mix changing, those durations and how well they fit the resource adequacy needs, those start to change pretty significantly. The hybrid resources, again, another reason why modeling resource adequacy across chronological operations becomes important because specifically on the hybrid resources and specifically when you start getting into things like the investment tax credit and charging constraints that you might have on the hybrid resources, you need to model those even if the energy storage needs to be modeled against a weather profile, right? And when you get into the hybrid resources, the availability of the solar will also influence how much charging you can do on the batteries and how much they'll be available in later hours. So that gets to be important. But again, I think you can mitigate that as you start to converge between production cost modeling and resource adequacy or reliability probabilistic modeling. And then the ancillary services, again, I think that just gets another layer into the modeling work that you need to do, is make sure you're capturing the ancillary service market mechanisms. And I think when you start calculating your loss of load expectation or your capacity shortfall events, you just need to make sure you're quantifying at the right point. So depending on the ancillary services, you may shed load before you violate spinning reserves, or at least a portion of the spinning reserves, right? So you just want to make sure that when you're quantifying those loss of load expectation events and hours, that you're quantifying it either before or after your ancillary service requirements accordingly.
Okay. I think we're going to need to wrap it up now. We're a little over the top of the hour. Still a lot of good questions out there. And as I mentioned earlier, an email is going to go out once the video file has been posted. And I want to encourage you to send any follow-up questions to info@esig.energy, and along with the ones that we weren't able to answer just now, we'll get them answered and posted as quickly as possible. We appreciate your engagement and look forward to seeing you at our next webinar, which will be held at 2 p.m. Eastern on December 17th with Ryan Quint of NERC. We'll be speaking on NERC's inverter-based resource activities, and hope everybody will be able to join us once again. Further information on all the webinars and meetings can be found on our website at www.esig.energy under events, and in our newsletters and informational emails, and you're all invited to attend. Derek, I want to thank you again for this very timely and informative webinar, and thank all of you for your interest. We look forward to seeing you later this month, and in the meantime, everyone, take care, stay safe, and thanks again for your participation. Okay, bye now.
Thank you, Charlie.